the area, which is the m dot t, and that is your boxcar function, and the tau is the rise time of the fault, right? So that is your m dot m, right? And this is your dislocation, and based on this simple model, the Brun has first computed the displacement equation of the displacement value at the site, right? So at the recording site. Now, here I am trying to provide you guys a relatively very simple mathematical concept to do all these things, right? The detailed mathematics is little bit yeah, okay. The detailed mathematics is a little bit complicated, but I'm trying to save it as a main concept that what we have to do. Now, the Brun, as I told you in your Fourier spectrum calculation also, that this type of sharp edge will create a lot of numerical instability in the calculations, right? So Brun has make a much more smoother transition, and according to him, he has make the model is just like this one. So this is basically the rise, but this rise has some sort of an exponential increase, and that will be doing pictures like this. So MBT, so MB, I am writing it as a Brun's model. So it is a M0 into 1 minus this t by t tau into e to the power minus this one into ht. So ht is a Heaviside function. And if you take the derivative of it, then this derivative will be equals to m0 t minus tau r into ht, and then calculate m dot t. Okay. So this is another way of expressing the dislocation at the fault. Okay. Okay. Now let us understood this one, that we are trying to do the far field expression. So far field means from the source, the station distance is relatively large. Why it is? Then basically the source can be treated as a point source, and it will be much more easy to express it just like the way we were trying to do, right? So we are trying to understand the far field seismic waveform, okay? And the 4 source parameters are basically plays an important role. First is the final displacement across the rupture. We call it as a D. The dimension of the rupture, that means length and width. The rupture velocity, that how soon the rupture is propagating, and the particle velocity, right? So this 4 parameters is very important to calculate that, and this is equals to 1 by 4 pi into rho. So the far field displacement value due to the rate of change of the moment will be equals to ur into rt, will be equals to 1 by 4 pi into rho. Rho is the density. Alpha cube is the p wave velocity, right? Alpha cube is the p wave velocity, and 4 pi rho into r to the power p divided by r, and this is what you have already learned in the stochastic modeling, that this is your radiation factor, which is the R theta in case of your in case of your stochastic radiation, and we have assumed it to be vary from 0.55 to 0.6. And this is 1 by R. It is the geometrical spreading, as I when I wrote it this time. And then m dot t into R by alpha. So it has been, t is the time at which this displacement pulse is calculated, but this displacement pulse, this m dot has been generated R by alpha times before the t, right? Because it has been generated at the source, so it is R minus alpha. So we have the t value because the t is the time where I see the displacement pulse. So therefore, this is m dot equals to t minus R by alpha. Does it make sense? So Rp is the radiation factor. So this is the simplest expression for the far field displacement. And m dot t you already know from your previous expression. Either you use the Brun or you take the either you take the Brun values. So you can put your TR, that means whatever you feel that your rise times are, and your tau r, and then this is your Heaviside step function. So it is going to be only one. So that you can put this as a MBT, or you can put it as a MT also. So that way you can calculate what will be the values, right? Now, so remaining time, remaining things is the TR or the tau r that you have to assume, and you have to give some values to try to see how your displacement pulse will looks like. So from there you can calculate the rupture time, right? Because you have the recorded spectrum. From the recorded spectrum value, you put these numbers and see whether the recorded, recorded time history, not the spectrum. Recorded time history, it's a time domain. So recorded time history, if you know, then we try to give all these numbers. So this density value, the VP value, and these things, and we calculate these things for the different values of t, and then see how it will fit with your recorded displacement time history. And from there, you can calculate your tau r values or the m dot tr values so that you can calculate, right? Okay. So now let's see. So you have okay. So since the fault has a lot of points, and they are all simultaneously got sleep, and the different values of sleep is possible for each, because this is the fault, and this is at this point, this might be at this point, at this point. So we can go on calculating this fault, and then we add. So the our total T will be equals to the T minus Ri by alpha. Ri means from the source, from the receiver point, you calculate this distance at a different points, right? So that is your Ri by alpha minus your delta Ti. So that means that the difference it will take to go from here to here, right? So that means the delta T, or the time sampled, you can put it and add them all together, and then that will be equals to your the total displacement all over the fault. Is it okay? Oh, so this entire part will be the mu into AI is the this this part, the URIT is equals to mu s into di dot. So that will be equals to mu into A, means W into delta X is the area. So this is your W into delta X is the area into di dot into T. So di dot you can calculate from this number, right? So therefore we can write your URIT will be, if you just put all the formula before, so RIP into mu into 4IP into lambda cube into W. So this is your W into di dot into Ri into T minus this into your delta X or the dx. So that will be your total calculations, right? But please remember, this is your displacement equation dot. So ddt or the change in the displacement. So this is your a property I will be using. It is called d dot t minus xvr. D dot t minus xvr means it's a delta t. So t minus xvr. So if it is a delta of t minus t0, you can calculate it is basically equals to the basically if you can multiply any things, say suppose any amplitude with a delta into t minus t0, so that means you are basically shifting it from 0 to t0, right? So that's basically you are doing the shift. So these things equals to, therefore, whatever it is at a time t, and then multiplied with a t into x by v0 with the delta values. So then that will be equals to d into x by v0, right? So you can put these things rp mu into 4 pi alpha q and then number w, and then give the r outside, and then this d dot into t, we can write this will be equals to from 0 to x. X means up to which this rupture took place. You can do this expression. So put this value RPU into this one into W by R. Now this dt is this is the convolution integral, and that is what I told you earlier, that this convolution we need to perform, right? So this is your convolution because this is a t minus tau. So therefore this is the convolution operation, and that convolution operation we have to calculate it out, right? So if you do this calculation, this convolution operation, we will be using that this is your a delta function dg over a time, over a time, these things. So ht equals to, if I do the integral of delta g, it becomes a Heaviside step function. So that will be equals to less than 0 and greater than 0. So this is your d dot t up to this much. It is all okay. This much is only here. So that part is fine. Then this part is fine. Up to this much is fine. Then the convolution, then this function is equals to, actually, if you do this integral will be replaced by ht, and then this will be h into t into x by pr, because that's your this functions, right? h0 equals to ht into this one. So this is this function, and this function means it is basically again, this is the box function, and that box function is this one, right? So that one is basically the tau c. Right, so that will be a tau c. So this tau c equals to t into x minus vr. So that is equals to your rupture time. Right, so you are basically doing two things. One is a box function, which is your rise time. this part is your rise time part, right? And then you are convolving with this, you are convolving with a function which depends upon the rupture. So that means how far it is going from one point to the other point. So each point it is rupturing, right? So that is your TC. So if you do these two box functions with a convolution, these box functions will be a trapezoidal function. Okay. So this two box function, if you are doing it like this way, you are basically, this convolution gives you a trapezoidal function with a rise time and the downtime are all TR, and this will be equals to TC plus TR, right? So the total time will be the TC plus TR. Oh, so this will be equals to TC plus TR, and that's the number. So this is your trapezoidal function. So boxcar function starts at time t and has a duration equal to the total rupture is that TC equals to x by VR. So if you know how far the station is and what is the velocity of rupture, the velocity of rupture means it is your x divided by 0.9, approximately 0.9 of the velocity of the P wave. So you can calculate what will be the TC value. So you have a TR value and then TC value. So this trapezoid will be basically a sum of the two boxcar, and that you can calculate, right? So the Haskell, this is your Haskell fault model. It is one of the simplest fault model, and that will be equals to URT will be equals to this much, and then this is your two things will be convolved with each other, and then you can multiply this part with this one. So UI by this part. So that is your, this equation will be equals to this one. So this is your convolution integral of two boxcar functions. If you can say that will be equals to mu dA, so that will be equals to mu 0. So the area of your d dot t is basically d. It is the total slip, right? So d is the total slip. D dot is the rate of change of the slit, and the area of these things, this W, V, and R into BTCO, this is basically equals to mu A. So this is basically the mu A, this part. This is the mu A, and this is basically the D. So mu into dA into this, so that will be the total moment of the values, right? So this is equals to m0 into this much. Right? So that's that. So therefore, this side is the seismic moment mu dA, and left hand side is the area under the displacement pulse, and that is corrected by this one. Now you can see it here. This is one of the earthquake, and if you can see that this is a displacement pulse, it looks like this way, right? So this is the plus, up or minus, that doesn't matter because that's the polarity. But you can see this is typically a trapezoidal part. So from here you can calculate what is your TR, right? So that's your rupture duration. You can calculate from here. Okay. Now, so this is one part, is the rupture calculation. Then there is another part, is the rupture directivity, in which direction rupture is going. That is also important things to understand, that uh, let's see that this is a oh, oh, okay. So let's see a rupture when initiated from here. So this is your first point when the rupture start, and then as soon as it rupture here, this signal is going to the recording station, right? And then over the fault, the rupture propagate, okay, and propagate, and it comes say at this point, then that is also going to the recording station, right? So one point it is going to the recording station, then the rupture propagate, and then that part also comes to the recording stations, right? And let's see the velocity of rupture propagation is the VR. And let's see, this is the length of the fault on which the rupture propagate, right? And the site is located at an angle of theta with the ruptures or to this part. So what is the so first, if you see that this velocity is c, I am trying to write it in a velocity values as a c. The c could be Vp, c could be Vs, right? That doesn't matter. So anything it could be. So I'm just writing it as a c, because along that path, the P wave will go, then the S wave will go. So that's part. So the c I'm trying to write here as a thing. So after this time, since the distance is r, so the time taken for this rupture to reach at the recording site is equals to t equals to r by c, right? And the c is the velocity corresponding to the wave type. So it might be P wave, it might be S wave. So that's that is okay. So now what is your the time difference, right? So time difference from this rupture coming from this point and the rupture coming from this point, right? So if we can call this Tc is the time difference. So this is your time difference of rupture, time difference of the wave coming from this point and wave coming from this point. If you can do that, hey, that Tch theta will be equals to your L by Vr. So L is this distance, and the velocity of rupture is Vr. So this is your L by Vr plus r minus L cosine theta. So this is equals to r minus L cosine theta will be this distance, r minus L cosine theta, divided by c, because that's the distance. So this is your L by Vr is the time from here to reach, and this is L by r minus L cosine theta by c minus r by c. So that's your difference. So if you can calculate, then this will be L by 1 by Vr into cosine theta by c. So that's the time of difference at the recording station if the rupture comes from here, right? So therefore, oops. So if you can see in that manner, okay, now let's see. What is the directivity part? And that is why it is important. So this is the fault. Okay, so this is the fault. On this fault, the rupture took place, and the rupture is propagating towards this side, right? Imagine you have a 4 station. One station is located on this side, one station is located on this side, one station located on this side, other station located on that side, right? So these are the 4 stations located. Now, if you see that, you have seen that the station which is located towards the rupture, so that means rupture propagation, and it is on this rupture side, then this will be a very big amplitude here, right? Although this magnitude is the same for the things, but in this case, in the station which is opposite side to the rupture, their amplitude is not that much, but their duration is the more, right? But the amplitude is not. Okay. Now what has happened is this, that, but if you can calculate the moment from this station, moment calculate from this station for this earthquake, they will be all same, because this is the magnitude, amplitude multiplied by area, and that will be always the same. So they have a less amplitude, but will have a long durations, right? So if you go on calculating the moment, it will be the same, right? And that is the same earthquake. And on this side, perpendicular side of the propagation, the amplitude will be like this, right? So this is a 90 degree, so cos 90 type of calculation. So put the value, the cos theta equals to 90 degree, then you can calculate that part will not contribute at all. So only this is your Lx by Vr, right? So that way you can understood. So you will be seeing that during a big magnitude earthquake, some part, say suppose from the earthquake source area, some part get highly damaged, but the same distance from the source, same distance, the other side has not get. So what has happened, sometimes you will see that the earthquake, some part get damaged much bigger way, but the same distance, the other part of other station site has not. Okay, and also the perpendicular to that station site has not destroyed that much because of the directivity of the fault. So the directivity of the rupture, if it is in one directions, then it will be very that direction, it will be very highly damaged, right? Because the rupture is on that directions. Yes, it could have reached the bits, and so that's the other. Here the other strand of concept. Yeah, to the point. You know, Doctor would be thing they try. So that skins. So we wash it, but I say it. But wait, in the zone, that chat, if it is a starting from here and it goes there, then it is going in the 1,000. You know, I just start at this point and was at the wood side. To use it on the biological structure. I'm going to and I'm better you can see on the working in the some of the older stations. You understand this is what you that to the structure by the Bible to the structure that it is will say would you be me when I had an amplitude or an amplitude is a nature that's in the biological world production, isn't it? And when they start just so that means that after isn't control, it is like a standard but the theory. And the guidance interpretation is also really on the way out. On the studies at the side of the modern limits. And so it is not into money that I becomes in limits. And so later is it to content and get affected by the directivity of it. I think wait a minute. No, it is very trust and also. You can see results from the previous inclination plan. Also, the through like in your Asian lines that can let us about the art part of the radiation factor in trying infinity to blood infinity your displacing environment. It is to story. This all equals to energy work. So that's the running so what way you can as a the symbol of the function. What is that? this ATT button of bullshit bar. We know what to this with the salary I get up the system, go into the orient hands every time I started. So I would handle this to it and now came to be TR, convolution be DC. So we need to other. This will be all the side function with the moment. We should talk in the pink eyes, and this is BTC. In Canada, they would that. They have a similar chance when you the time open. So the ages of it ain't all red. That is in can be considered. It's the first time. Because this in a simulation when it's the spectral density. So to make this to the bolster down. I believe necessary box our function. The sub function is actually it was function in actually input one use what we quarterly does it. And it was function just like the Oscar function can not understand function this function it is called single function, right? This function it is called sync function, and this is also our best sync function. This sync function has any DLC or that in the distribution and modification wise tradition and that are exactly and it can declare the significance on the of the sun with it so from Ross things the other point about turtle this. And this will be United States the only line to do. So we acted in the different transform of with the theoretic and in a tangle of it. There is really the same function on that. But the position all the same function by indication. They are need to be the same functions. Okay, so this same function, this if it is a when the omega t by 2 and when omega r by 2, then that will be equals to 1 if omega is less than 2 by tau r. That's the same function property, and it will be equals to 1 by omega t r by 2 if it is omega going greater than t by 2 r. So that's the part. So since it's a two-box star, L will be equals to M0 for omega less than 2 by Tc, and M0 divided by omega r by 2 between these two values, Tc and Tr, and M0 divided by this one between these two values. So basically, if you see the source function, then it will be flat for the period of rupture, but the rupture time of the fault. If it is the if the period is longer than the rupture time of the fault, then the source function becomes flat. Okay, and then it will be decay as 1 by omega for periods between the rise time and the rupture time. So between the rise time and the rupture time, they will be fall as a decay as a 1 by omega, and decay is proportional to 1 by omega square if it is greater than this one, right? So these functions will be looks like this way. So if you can see it here, this pictures. Oh my God, this picture is also not visible. What has happened to this page? I don't know. So if it is a bilateral or the by the two boxcar convolution, the one is the TR and other is the TC, then you will be seeing that this will be the dw omega the length of the rupture TL, and then this will be it is the length of the rupture propagation, and this is the rupture propagation along the dip direction, so that will be equals to TW. So that will be the m omega values, right? Now, so if your source function, whenever I saw the source function you have seen in the stochastic modeling, that this will be equals to m0 into 1 by fc to the power n equals to 2, right? So this is your fc is the corner frequency, and this corner frequency is the corner frequency is equals to that this number. So if you know if your rupture is a circular rupture, or it is basically a point source, this corner frequency for S wave, if you do the S wave part, then this will be equals to 0.2r into the velocity of the B divided by the radius of the fault of the rupture. So if you know your corner frequency very nicely, or if you can find out your corner frequency fc from your displacement pulse, sorry, I take it back. If you can see your corner frequency very nicely from your displacement pulse, if you see your corner frequency in your displacement pulse very nicely, okay, so then if it is fc, then if you can put that fc values, and then you know the vb, the velocity, the beta value is equals to the, say, suppose 3.4 kilometer per second, and calculate it, then you can find out what will be the your radius of rupture. So how much is the rupture radius, you can calculate, and that will be equals to 0.21 into velocity of this beta, and then divided by FCS. So if you know that, you can calculate radius of rupture. So or this radius of rupture, as I said, this will be related to 0.42p into delta sigma by m0 1/3. So m0 fc cube equals to 1/3 values, right? So so from the source spectrum, you can calculate, or this your TR and TC values, you can find it out, and the TR, TC, how they are related with the magnitude, you can, this tau c, the tau values, how they are related with the magnitude, you can find it out. So this is 1 by tau is basically your the frequencies, right? So that you can calculate, and m0 fc values for the different delta sigma. So that means this is your delta sigma at the different values. You can calculate the magnitude mw from that. Okay, so this is your spectral part, and that is what you have observed in your convolution with your displacement pulse. So this is your displacement, and that is your amplitude. Then this is your the source time function, and this is your propagation path. So the source time and propagation path is convolved, and that will be the multiplied with the amplitude part. So if you can take it in your the spectrum domain, then the spectrum domain, these are all multiplication with this one, which you have read it in your stochastic simulation. So there is a constant term or the magnitude term, then there is a source function, side function, and the path function that you can use it that. And if you take the log of all these things, so log of UW will be equals to log of F. And since it's a multiplication, so it is a plus of this minus of this part, because this is divided by this, and then this is your plus of log G part plus of log PXW. So these things are the logarithmically, this is just a linear, this is the linear relation of the source, path, and the site, and the propagation path, right? Now, if you can see here, a small magnitude earthquake and a big magnitude earthquake, say suppose 8.1 in Mexico, and there is a 3.1 in the things, how the how the difference are. So that means when here there is a lot of long duration thing. As you go from here to here, when there is a lot of magnitude. So this is your actually the main shock, and then after that there are a lot of when other shocks are coming, and this is your centimeter per second square is the acceleration. And if you can see, if I can put this spectrum domain, so then if it is a 3.0, the spectral frequency, the corner frequency is here, because this will be like this will be like this will be like this, this will be like this, and then this will be like this. So as it goes to the corner frequency, as the magnitude increases, the corner frequency basically goes shifting towards the lower frequency side, and the amplitude of the signal is now much higher, right? So this is the same thing if you plot the spectral domain, the spectral I think they are plotting it. It is the velocity response. So they are plotting it as a PSV value. So then this will be all like this. So that means if it is a small magnitude, then amplitude is equals to here. And if it is a large magnitude, 3.1, then this will be here, right? So we have learned that if you have the displacement, so that displacement will be equals to 1/4 pi into rho, right? So that part will be common for everyone. 4 pi rho, 1/4 pi rho, 1/4 pi rho. These are all same. And this is for this AN, this is for the near source effect. And then this is the intermediate P wave. If the distance is intermediate, then this is the intermediate is the P wave, this is the intermediate is the S wave, and this is the far field of P wave, and then this is your far field of S wave, right? So this is actually we have done. These two we have calculated. So this is your 4 pi alpha cube, and then AFP, and this is m dot T into R minus alpha, and this is for the P wave, and so it is alpha cube. If it is a S wave, then it's a beta cube, right? So this is, so if you can add all the contribution, then it will be like this, right? So these are all the description of the numbers, so you can see that. So both the U is the displacement, X is the distance, both are vector, and we are assuming X equals to when 0 means at the center, and T equals to 0 means at the center too. But this is your time at any time scale t. So we are saying that your this is your basically your m tau into m0. So this is the function. So you can put it here 1/r. So this is your near field term. So if you have a very near field, you can only take up to this much. If it is an intermediate field, then this will be 1. You can see this is r square. This will be the r4. So intermediate path, intermediate thing 1/r square, and this is t by r by alpha. So that is your distance traveled, right? So this is your intermediate S wave. So this is your intermediate S wave will be equals to this. Intermediate far field P wave is this, far field S wave is this, right? So that's your displacement, and these are the radiation pattern, right? So AFP, AS, these are all the intermediate path radiation pattern, and then these are the AFP, AS, these are the far field radiation pattern, and the radiation pattern values are like this in front of the theta and phi. Theta is the angle distance, phi and these things you can calculate. So that will be equals to this much. So this is the angle by which the recording station is located from the source theta value, and this is your phi value, which is the projection of this one, right? So if you can put these values, and this alpha and beta are the basically the velocity of the P wave and S wave, and rho is the material density. Now you come to this part, right? So m0t minus tau. So m0t is the basically the first derivative which can control the shape of these things. For the far field, you are getting m0 dt. For the far field, we are m dot this one. So these are called time derivative of the moment. So this is your time derivative moment, time derivative of the moment. So this is what we call it as a moment rate function. So this is what we call it as a moment rate function. Okay, so this is m dot t r alpha, so that you can calculate. So m0t is equals to mu at into dt, and m0t is equals to 0 when the earthquake begins. M0t becomes m0 when the when earthquake is finished, right? So m0t is a treat as a process from m0 to your m0. So this is your value of m0. So m0 starts from 0 and m0 finishes at this point, right? And this rise is the tau, which is the rise time from the 0 to m0. So this has to be divided by 1 by r4 for the near surface. But if it is a far, then it is 1 by r. So that is your geometric spreading. This is your geometric spreading 1 by r, and that you can calculate from this one. So so this is the signal. So r alpha for the intermediate P wave and for the far field P wave, this difference is basically the faulting delayed by the P wave, and this is the faulting delayed by the S wave from the intermediate station or my intermediate side to the far side. So this is the signal for the duration of the faulting delayed by the S wave part, right? So if it is a moment function is equals to a function like this, right? So if I take the m dot t, then it becomes a functions like this. So a functions which is a like this, if we take the m dot t, it will be like this, right? So m dot t is basically related to the displacement pulse, right? Far field displacement pulse. So you can see it here. This will be the far field displacement pulse is m0t. So that will be like this, right? So m0t suggests the simplest possible shape of the far field displacement pulse will be like this. So that means if you see a record, and that in that record the displacement pulse looks like this, then you will be seeing that this is basically your tau. That basically your tau. So that means that will be your things like this, right? So if you see that this is your m0t, then it will be like this. So then m dot t, it will be like this. So this is your displacement pulse, far field displacement pulse. And if you see again differentiate this, then your velocity pulse will be looks like this. Any velocity far field pulse will be looks like a positive up, a negative up, or a negative up corresponding to a positive up. And then if you can do an acceleration record, you will see the pulse when it will be like this. Okay, so that is basically your tau. So from here to here, that will be your tau. So by seeing your record, you can very easily can identify what is your tau value, and then this tau is equals to 1 by of fc, right? So that is your corner frequency. You can easily find out by seeing the pulse, right? So this is your velocity pulse, this is your acceleration pulse, and this is your moment values. So by seeing the, similarly seeing the p pulse, you can do that, and you can also do it by doing the uh, by the far field pulse, but this has to be the far field, not the not the near surface things, or near source things. So if you see your uh, S-wave far field station, so then you will be seeing the velocity pulse will be, sorry, your displacement pulse will be like this. So if you can use that, and then m0 by 4 pi q, this one, by seeing your velocity pulse displacement values, you can calculate what will be your m0 values, right? Or we have already seen that if you take the Fourier transform of that, then you can find it out like this, right? So if you see your if you see your displacement pulse in a time domain, it will be like this, right? So that will be like this. So this is your displacement pulse in the time domain. If you see it is in a spectral domain, then the spectral domain, this displacement pulse will be looks like this. So that will be equals to your fc, and it will be decayed by f minus 2. So that will be, this decay will be equals to f minus 2. So that is what we can call it as a omega squared decay. So decay by omega square. Now, if you have a velocity pulse, then in the far field, the velocity pulse will be like this, right? Far field velocity pulse will be like this. So if you calculate the time from here to here, then that will be the time, and your velocity pulse will be equals to like this. So then it will be like this, and then it will be decay like this. So this is your corner frequency in that case, right? And if you see your acceleration pulse, the acceleration pulse in this one, it will be like this. And if it is a time domain things, then you can calculate this time, and then if you see, then this will be like this. So this is your fc, and this is your f max of these things. So if you can differentiate this one, you will get this one. If you differentiate in the frequency domain, you will be getting this one, right? So this is your point source, and so you can take the Fourier transform of the boxcar. It will be minus d by 2 to plus d by 2. Then this will be always a functions like this. So these things, if you can calculate it, it will be the boxcar function, or it is a Sinks function in a frequency domain. So this will be like this, and this is all 1 by d and all these things. So if you see the plot, this plot will be, if it is a box, then you can find out that this will be the corner frequency, and this will be decay like this. So if it is a corner if it is a box like this, then the corner frequency will be at this point, and then that will be 0. So if it is this one, corner frequency is like this. If it is a thin pulse, thin box, then it will be much more relaxed type of things. If it is a very big box, then it will be very sharply in a frequency domain. So this is in a frequency domain. So in a frequency domain, it will be like this, right? So if you can plot this one, it will be decay. This will be the corner frequency, and it will be decay. But if it is a very thin pulse time domain, then the frequency domain, this broader, it will be much more broader than this one. So it will be looks like this, right? So for this, we have this discussion for so far. So spectrum is flat at low frequency, then start to decrease at a corner frequency for the displacement pulse. And we will treat this corner frequency as a half of the frequency of the first zero in this case. So it will be equals to 1 by 2d. And we can, the corner frequency is inversely, the corner frequency is inversely related to the duration of the sleep, right? And you can, this is your L by VR is the duration of the rupture, and this will be the time. So you can find out from here, this is your point source and this is your radius of things. Somebody was asking me about the stress drop part. So in case of your stress drop, this delta tau, which is the static stress drop, this will be equals to d by w. So d is the your rupture, and then w is the wind, and c, and this is your mu is your this part. Now in case of your circular rupture, delta ts equals to 760 by mu into ds. In the strike slip fault, on the delta ts or the stress drop will be equals to this, and for the normal this will be equals to this, and we are assuming the lambda is not equals to mu. So but mostly the equation is delta sigma equals to 7 by 60 m0 by rb, and rb we have already calculated something around 0.2 b, or the Brun radius for the rupture will be equals to this. So if you know the Brun radius from the fc values, you know the moment from the top here, you can calculate how much it will be the delta x. So this is one of the numerical example. So we have taken the S-wave spectrum here, and then we calculated the S-wave spectrum, a displacement spectrum from here, because this is your acceleration values. So we calculate first the acceleration spectra. So we calculate first the acceleration spectra, a omega. So this is your acceleration spectra, and then we have calculated the a omega. We have divided by with a omega square. So we divide the omega square, then it will be a displacement spectrum, right? So if I can divide it with the omega, then say this thing. So then from this one, so this is your low frequency side, I put it here. So that will be equals to 10 to the power minus 2, and calculate this number, because that value will be equals to m0 fc 4 pi into that number, whatever I have given it to you. So you calculate this number from here, and then m0, you can find it out because you know the rho, beta, r, everything you calculate, because r is the distance. You know how far is this station. So you can find it out, this one, and compute your m0 value. So m0 value we can calculate 10 to the power 22, and from there you can find out your mw by using this, the mw equals to 4.2. So so we first need to find out what is your fc, and from this fc we can compute that this things is basically by seeing the record, I can take the Fourier transform. I can calculate your m0 value, mw values, what is the magnitude of the earthquake, what is the moment of the earthquake, what is the corner frequency, and what is the therefore the duration of the earthquake. Everything I can calculate it out, and this decay I can also find it out. This decay has to be equals to f to the power minus 2. So this is what we call it as a omega squared decay. So that we can find it out. So by seeing this number, we can get how much is the decay after the crossing frequencies, right? Or the cross FC values. So this is the example of the uh, computing the Fourier transform of the data, right? So this, okay, I'm also finished. So this is what you have to do. So in case of your S-wave, you can plot the S-wave spectra, and from the S-wave spectra, you first differentiate it. That means divided the S-wave spectra by 2 pi f, the 2 pi frequency, and compute the displacement spectra, plot the displacement spectra, and that displacement spectra, from the displacement spectra, calculate the low frequency amplitude, and from that amplitude you can calculate the M0 values, and from the M0 values you can calculate m omega by using the M0 m omega relation, and that is what, from the recorded data, you can find out the actual earthquake moment and all these things. And this can be done very routinely. So that means as soon as the earthquake happens, S-wave has been registered, you can write a script which can immediately tell you what will be the omega values by seeing the spectral data, right? So that is what we are basically at the observatory. They do that. You try to calculate the moment information very immediately, and also from the spectral data, from the time series data, you can also have an idea about what will be the corner frequency, and we can also get the corner frequency from the spectral data. So these are the information about the source, and we have also told you about the site. So these are the most important factors for the things, and we will be touching upon a little bit on the path factor or the Q calculation that will be done in the afternoon sessions. Okay. So any questions up to this much? So looks to be a little bit complicated, or what? But that's when you did computer in TikTok. Something.
So it is a very structured and very nicely comparison. And you for that by bringing some work that were to do the process every 2 months.
Yes.
But it's nicely made up.
With our different streams. And you can certainly
So nice. And I'm going to
participate in that much of it. So I felt it's what thing is not the nation that I'm kind of
hitting what's happening.
it's by taking good at it. And
Losing to Lahan the way like I
knowing the things. And well, the mistakes, but in
gets a band
again, around it. So in my that's the part. But I think I can figure this sequence in these there are not
as I have to release.
when you find that something for about
Lot of
things in irony
that are not
monitoring that it can be mathematics,
but
a symbol that things is this much. So if we can understand each one, add some position about this one, then we can whereas the in a standard seismological work, and then understand the rest of the things.
giving it in.
When he is doing it. So you can ask me together that I cannot finish the book in a 10 days of the time, because there are a lot of things which you need to know, and also some lot of mathematics, digital signal processing principles that you have to understand before you say like this. But it will be gradually done if you have a full a rough sketch is in front of you. Okay. Thank you. Thank you.
Principal.
You can say that. There's somebody that's telling me this one. Oh, yeah, something. So that kind of things.
So okay, this is going to be a base, not to standards.
That that you can see that the soundbite did that. Okay, thank you very much. We'll meet you at 3 o'clock.